About LAN extension and virtualization using layer 3 protocols. It turns out there is a lot of overlap between virtualization and cloud computing. So by the time we finish all this virtualization, we have probably finished cloud computing as well. We'll have so for clouds we need virtualization, and LAN extension is one of them. So let's see what is LAN extension. So basically we'll talk about what is LAN extension, and then today we'll talk about two protocols, TRILL and LISP, and then next time we'll talk about the rest of them, which is NVO3, VXLAN, NVGRE, STT, etc., etc. So just to remind you where we are, if you remember, there are lots of things which are being done for virtualization, just too many. And so we are going to cover as many as we can. So today, in this module, we are doing TRILL and LISP, which belong in here, extension or aggregation, okay, using layer 3. We did little bit of MPLS, VPLS, etc., before. PW, this was pseudo wire, etc. before. So this was the part which was left over. And then next module we do this part here. And if we have time later on, we do the other modules. But so here we are. We are going to talk about how to send traffic, L2 traffic over L3. And so basically, why do we need to do that? Because the data centers could be located in different places. And if you have more than one data centers, you want to be able to use them all at the same time for the same problem. In case one goes down, you should be able to move all the traffic to the second one, or use both of them at the same time also. When you have two of them, you have three choices. You could have cold standby, which means that the second data center is just waiting, is not really doing anything. It's cold, means it's not hot, means it's not really working at all. So data is backed up on the tapes and stored off-site. And if there is a problem, you bring the tape in and you run it, and that is what we used to do 20 years ago. Right? We don't use tapes anymore, and we don't do cold standby anymore. So what we do is hot standby. In hot standby, we take two servers, and then we exchange the data and the state continuously. So they keep track of what's going on. Okay, but it is still standby. See the difference between standby. So the second data center is not really doing the same job. It's just keeping track of what the primary data center is doing and just copying the results. Okay, so that is hot standby. Two servers, synchronous or asynchronous data replication. Now synchronous and asynchronous, we had talked about this before. Synchronous and I don't know if anybody remembers now. What is a synchronous replication or synchronous write? Anybody remembers that? Yeah. At the same time we write before we return before we return the write, we have finished on both. Right? In asynchronous, we write on one and we return, and the second one is queued. Right? So that is asynchronous. All right, good. So replication. On a failure, the application automatically switches to standby, and this is what we did up to 10 years ago or 8 years ago. The problem with this method is that you are losing half of your resources, because the other half of the resources are just sitting there. Right? And so what we do now is active-active. And active-active means that everything is used at the same time, basically, and whenever you basically run into trouble, you just use half of them, in the sense that you have let's say two computers, one here and one there. So you are using two computers. When one fails, you just use one computer. Obviously half of the job will not be done, but you have not wasted any resources, and you have been able to continue whatever is most important on the one that you have. All right. So the active-active means that both things are being used for real jobs. So you understand the word active active and standby. Standby means it is just waiting. Active means it is doing something. So if I hire two people, I give them two different jobs to do, and then if one fails, then I give the most important job to the one that is left. Okay? Any questions about that?
So
Yeah.
in the active case, then the different machines can run different jobs at the same time. I mean, in the active case,
Yeah.
are they running the same task or the different task?
Oh, yeah, right. So you don't do the same task. In some cases, you need to do same task. For example, in Hadoop, we do 3 places same task. But that doesn't have to be different data center. It could be in the same rack, right? But here we are talking about the data center availability, right? So we are not going to do the same task in 2 data centers. Okay, all right. So the data center interconnection problem is that you have 2 data centers and you want to connect them. And since you want to be able to move VMs from here to there, you want both data centers to be on one Ethernet, right? That means on same L2 domain. Everyone understands that, right? So everybody understands now that same L2 domain means one Ethernet, so that you can move anywhere. And this can be used for disaster recovery, for maintenance or migration, for high availability, for consolidation, whatever reason you have 2 data centers, and so you need to be able to make one Ethernet out of them. And that way, when you move, they can use the same IP. They don't have to worry about changing the IP. And multicast can also be used if basically to different destinations. So this is the data center interconnection problem. So today we actually talk about something like this: data center interconnection, or LAN. This is also called LAN extension. Now the problem with the LAN extensions are, first of all, broadcast storms. If you have a LAN which goes to many machines, 10,000 machines or 20,000 machines, then you have lots of broadcast, and the broadcasts are flooded, right? Actually, the whole thing we call it BUM: broadcast, unicast, and multicast. All those 3 traffics are flooded, and they can cause broadcast storm. Then you have big networks, means you can easily form loops, and therefore spanning tree gives you a lot of trouble. We have already discussed this. High spanning tree diameter, and then the new problem is that with big network like this, the diameter of the spanning tree becomes very large. That means the path from the leaf to the root. From the leaf to the root, that is called the diameter, the maximum path. That could be more than 5 or 6 or 7, and that means, if you have a tree which is 7 deep, you can imagine how much traffic will go through the root. And so you don't want that kind of stuff where the tree is very deep. So root can become a bottleneck and become a single point of failure, and multiple paths remain unused. The bigger the tree, the more paths are there. Yeah.
What's the minimum? 7?
Minimum what?
7. More than 7 days.
Yeah, more than 7 is the diameter. So I just explained what is the diameter. Does anybody remember what is the diameter of a network?
From leaf to root.
Yeah, the maximum distance number of hops from the leaf to the root. And so if a tree is 7 deep, that we call a diameter is 7. Actually, it should be called a radius, but
The depth is 7.
Huh?
The depth in the tree, the
Depth of the tree is 7. Right? I don't think they define anywhere. I can go and check the definition. That looks like what I defined is radius rather than the diameter. Diameter should be leaf to leaf. Right. Going through the center, which is the root. But my understanding here was that 7 is the depth of the tree. Okay. Then we defined tromboning. Actually, tromboning was in this slide, which actually we had skipped this set of slides before, but I will redefine what is tromboning. Basically, what happens is that if you have data centers which are very far apart, then your default gateway might be in this data center, and you are in this data center. When they had designed the default gateway technology, at that time they didn't really think. They thought that everything on one Ethernet is very close, 200 meters. If you have 5 routers, it doesn't matter which one you go, so you randomly select one router as a default gateway. Right? And that was good then. But now, if you are 5 kilometers away, then you really, if you have 2 routers, then it is better that the routers, the nodes here use the router which is on this side, and the nodes here use the router which is on that side. Right? But that cannot be easily done because the whole thing is one Ethernet and one subnet. And so what happens is if you are here and the router is there, then your traffic, first of all, it has to be sent to that side, to your default gateway, and then the default gateway will send to you. When you want to send it back, response, you will have to send it back again here, and then it will go out. Whereas you could have gone out from here. Right? So basically you are just jumping back and forth between the 2 data centers because your gateway is on the wrong side, and so basically 100% of the external traffic goes through this path. And security, basically because this connection is going to the public domain, to the public property. This might be across the street, or might be across the town, or might be across the country. And therefore, you have to encrypt everything that goes on that extension. All right, any question about any of these issues? So one of the first solutions for LAN extension was called TRILL, Transparent Interconnection of Lots of Links. Now, interestingly enough, this solution was done by Radia Perlman. C is the inventor of a spanning tree, right? And C is the killer of a spanning tree too, because this basically says that forget a spanning tree now. And so basically allows a large campus network to be a single extended LAN. So her idea was not so much about the data center. Her idea was for a large campus. So a campus like our university. It is several miles wide, and generally we will have lots of Ethernets here. We will have one in computer science department, one in electrical engineering, and maybe multiple in computer science department, and so on and so forth. Very little tiny Ethernets. And because of that, it makes mobility difficult. Every time you go from one Ethernet to the next Ethernet, you lose your connection, and then you have to start everything again, all over. In fact, when I come from office to here, we lose the connection, right? So all the FTP or whatever was going on before has to be disconnected and reconnected again. So she said that there are LANs are good for something and their IP is good for something. Why don't we take the best of both worlds? Okay. And so she says LAN is good for mobility, but then they have lots of other problems. First of all, they have very inefficient path using a spanning tree. Now remember, this work started before shortest path bridging. So this started 4 or 5 years ago. So at that time, spanning tree was the main thing, and then so the issue is that with spanning tree, if you want to cross a large campus, you are going to be totally off the optimal path. Inefficient link utilization, since many links are disabled. We know this problem with the spanning tree also. Inefficient link utilization, since multipath is not allowed. And then unstable. Small changes in the network, large changes in the spanning tree. When something breaks, we lose a lot of time, and we lose, and the whole network becomes different. On the other hand, IP subnets are good for all of these. IP subnets are not good for mobility because IP addresses change as the nodes moves and break the transport connections, but IP is efficient, optimal, and stable. So all of these are not a problem with IP. And so therefore, she said we should take the best of both worlds and we should use the MAC addresses, which is what allows mobility, but use IP routing. Okay? And so she invented a word called routing bridges, R bridges. Routing bridges, what they do is, these are R bridges right here, what they do is they take the packet and then they route it to the destination. So a normal bridge will take the packet, put it on the other side, this will take the packet, put it on the other side, it will go to the route somewhere and then come back down the route and then go to the destination. But instead of doing that, R bridges will take the shortest path to the destination, right? Because they are going to use IP routing, like OSPF or something. So R bridges encapsulate the L2 frames and route them to destination R bridges, which decapsulate and forward. So Ethernet frame is encapsulated into some packet and appears over here finally, and then it is decapsulated, so the real nodes see only Ethernet packets. Header contains a hop limit to avoid looping, and obviously, just like in any IP packet, there is a time to live field, which is the number of hops. R bridges run IS to compute pair-wise optimal paths. So how do they find the path? By using IS to IS. Why does it sound like that we have discussed this before? We discussed IS to IS, right? For what context was that? Anybody remembers? Yeah, exchange routing information. So that is what TRILL is doing. So basically, okay, anyway, so what happens is that this bridge will learn the addresses just like the source addresses. It will learn and then it will pass it on to the other bridges and saying that I know that these nodes are to the left of me, so I am the destination for them, and so on and so forth. So whenever somebody sees a packet going to H1, it will send it to RB1. Okay, so these RB4, RB2 and RB3 will not learn H1 by source part, they will learn it by messages coming from RB1. Is that clear? Yeah.
But isn't RB2 also connected to H1?
Yeah. So RB2 will also say that I have learned that the H1 is on the left of me, so I am also a path. Yes, there are multiple paths. So when somebody wants to go from H2, well, from H2 I think this is the shortest path. From let's say from here you have two hops, right? And there are two hops this way too. So there are two paths from this segment. So everybody advertises whatever they learn, they tell their other people, and the other people basically use the shortest path methodology like OSPF or something, whatever it is, and then find out shortest path for every host. Okay, so R bridges learn MAC addresses by source learning and by exchanging their tables with other R bridges. And each VLAN on the link has one and only one designated R bridge using IS to IS selection protocol. So now this answers the question that was before. Sorry, I should have read the last line. Last line says that when you have two bridges, one of them becomes the designated bridge, and the other, so basically for each VLAN there is one designated bridge. So there are two bridges here. For some VLANs this might be designated. For other VLANs, this might be designated. Okay, and that's how the traffic will be distributed. The load will be distributed between the two bridges. Okay. So this paper was published in 2004, which is 9 years ago, and the TRILL RFCs are just coming out. So that's how long it takes for things to get standardized, believe it or not. Yeah.
Is the routing is here is IP routing or is it just a layer 2?
Right. So routing here means that see, first of all, there are several parts of making the routing table. First one is to find out who is where, which is done by IS to IS. Right? Once you have that information, then you have to run some Dijkstra, some algorithm to find the shortest path to the destination. So that is run here. Okay? I mean, you could call that there. This is what is done in OSPF too. In OSPF, you run the Dijkstra and you find out what is the shortest path. However, we will not call it OSPF here because OSPF has more than just Dijkstra. So you run some algorithm to find the shortest path. Once you have that, then you basically just look at that table. So it's not like IP. In IP, you have the largest prefix match. Here you have exact match. Because you have 48-bit destination address, you look that up and you find that, okay, this is on this place, send it there.
My question is actually is it layer 3 or layer 2?
Okay, so this one is actually not very clear. I will tell you why. Because we use IS to IS, which can be called layer 3, but we are not using. Let me just see one more time here. Yeah, so we are not using IP as such. No, see, the next slide is coming up here. So the TRILL, this is the TRILL packet. This is the original packet. You put this header and then you put another Ethernet packet here. Alright? There are two headers. So the TRILL header has the source and the destination, number of hops to live, and the length of these options here, multiple destinations. This is multicast or single cast, unicast, reserved, and version number. So basically there is no IP here. Okay? So you take this, put the TRILL header, and then put the outer header, which is again Ethernet header, outer Ethernet header. Okay? And so this will find its way from source to the destination using these R-bridge addresses.
So if we had purely L2, then probably the R-bridge will learn only the address of the next router on the route, because we are having end-to-end communication. That's why we say it's like L3.
No, okay, hold on. Here's the thing. So this RB1, when it finds a packet, it will encapsulate it and say that it has to go to RB3. Alright? Now the path to RB3 is via RB4, so it will just give it to RB4, but really it is going to RB3. The destination field is RB3.
Yes. So, but does it know also the addresses of all the...
Yeah, right. They all know each other, yeah. They all know each other. In fact, this is what is happening here. The outer header has the address of RB4. So it will go from RB1 to RB4, and then it will go from RB4 to RB3. Now they will know that they reached the destination. Now they will take it off and give the original packet back here. So basically on this Ethernet, it will travel from RB1 to RB4, and then RB4 to RB3. Okay? So they know the path, they know the intermediate hops, they know the destination address. Okay? So even though this is under layer, did I say layer 3 before? But basically all layer 3 part is here that they are using IS to IS. Okay, IS to IS is considered as a layer 3 protocol in OSI terminology, although we use that in SPV. That's why I was thinking where we use the IS to IS. So this TRILL, while it was going on in IETF, IEEE already took it and adopted it and made it a standard. I mean, not TRILL part, the shortest path routing. That's where we were talking about IS to IS. Remember, we talked about very similar idea there in shortest path routing, that the bridges exchange addresses using IS to IS. That's what I was trying to say. That looks like we had talked about it. So that was SPB, shortest path bridging. That's a standard. TRILL is just coming out. The TRILL RCs are just coming out. So probably IETF is much slower than IEEE. All right. So let's see. Did we miss anything? For outer levels, outer headers, both PPP and Ethernet headers are allowed. PPP is the point-to-point protocol, and that is basically when you have point-to-point link, generally telephone links, we use PPP, and Ethernet is allowed, and PPP for long haul. If you are going to connect to long haul through telephone line, then you use PPP. Outer header can have a VLAN ID corresponding to the VLAN used for the TRILL. So the outer header, if it is Ethernet header, then Ethernet header could have a MAC address and the VLAN address, VLAN ID, and that would correspond to the TRILL VLAN ID. So this will say this is for use of the TRILL routers only, and nobody else can see that traffic. And then priority bits in the outer headers are copied from the inner VLAN. So now in the outer header there must be a priority field which says this is a high priority packet that is taken from here. So if this is original packet is high priority, then the outer packet is high priority. If it is lower priority, the outer packet is lower priority. Do all these three sentences make sense to everybody? All right. So TRILL features. First of all, it is transparent. No changes to capabilities. So the bridges, the nodes, everybody, not the bridges. The nodes work as if they were connected to normal Ethernet, and they go basically, and the bump traffic is supported basically, and auto learning is supported. Zero configuration. There is nothing you have to tell our bridges. You just connect them and then turn the power on. They will discover who are they connected to and what are the addresses, etc. Everything is done manually. Automatically. And host can be multi-homed. So now here is another interesting part, is that you could have a host which is connected here as well as here. Everybody knows what is multi-homed means? Multi-homed means you could have two Ethernet cards in a host and they could be connected to two different networks. Yeah. Multi-homed. Multi-homed means you could have, generally we are single-homed. We have only one Ethernet card. Right? But if you take two Ethernet cards, if you take one external one, one internal one, then you are multi-homed. You could take 3 or 4. So you remember in the data center, each server has how many homes? 2. So they are all multi-homed. Right? Because they go to 2 different switches, which go to 2 different this and that, right? So that is what multi-homing means. Dual-homed. We call it dual-homed, but multi-homing could be triple-homed, quadruple-homed. So that is multi-homing. VLANs are supported, optimized route is there, no loops, blah blah, and the legacy bridges with spanning tree in the same external LAN. This is the interesting part, is that you don't have to change all the bridges to R bridges on day one. You could have some old bridges which don't know anything about the R bridges, and some new bridges which are R bridges. Alright, how did that work? Let us show you. So just assume that some of these are not R bridges. What will happen is, let's say this RB4 is not an R bridge. Then this bridge will advertise all of these hosts and these hosts, and this will advertise same thing like that. And then when something needs to be going from here to H2, it will send it here to RB3. This bridge will will forward it normally because this has a normal Ethernet header going to RB3. Remember, the outer header is a normal Ethernet header. So this legacy bridge, the old bridge, will not know that this is a TRILL, and I don't know what TRILL is, because TRILL packets look like Ethernet packet to begin with. Right? So this old bridge will forward it to RB3, and then RB3 will open it up and send it out. So that's the beauty of it, is that it's totally compatible, totally transparent. The old bridges, and they could be using a spanning tree and everything else.
That would not even look at the TRILL header, only with the destination address.
Yeah, see, that's the thing is, TRILL header, they will look at the outer header only.
The destination address is there, but use that.
Yeah. VLAN ID, the priority, and all the MAC addresses are all here in the outer header. Okay? Alright, if there are no more questions, then we come to the end of TRILL. And the TRILL summary is that it allows a large campus to be a single extended LAN, which large campus now could be multiple data centers. And packets are encapsulated and routing using IS to IS routing. Now, we have to define what is IS star routing. Basically, IS star IS is used for exchange of the addresses, and then they use protocol or some algorithm to find the shortest path. And so this is in some sense similar to shortest path bridging. I think IEEE just probably got the idea from TRILL, and before IETF could finish it, they already got it in. Alright, so the second protocol that we will discuss today is called LISP. Locator ID Separation Protocol. So each host has an ID and a locator. Okay. For example, my ID is here, Jain, and I am located in Vashu today. Right? Last week I was located at some other place. So the ID does not change, but the locator changes. So in IPv6, you see we already have enough bits, so the first part could be locator and the last part could be ID. In IPv4, we don't have enough bits, so we have to give some number for locator, which is 32 bits right here, some address, and some 32 bits for ID. Okay, so every node has an ID and a locator. Locator is basically for the site where they are, and the ID is their ID, which does not change as long as they, whenever they move between sites or whatever, the ID does not change. So inside the site, if you are inside the site, then the routing is based upon ID. So when I am in Vashu, somebody wants to send a packet, it is done by looking at my ID. But when I get out of Vashu, then to go to wherever I am, then they will have to find out first my locator, current locator, which last week was Chennai, for example, and then they will find out how to get from here to Chennai, and packet will be delivered there, right? So that's the two parts. So the edge routers encapsulate the packet with the locator on the outer header. So basically, it's shown here. Bob is here. His ID is 1001, and the Carol is here. Her ID is 2002. All right, and Bob happens to be at this site, and it has a locator of 100,002, which is New York. Carol happens to be at Los Angeles. Her locator is 185,003. All right. So locator is where you are, and the ID is who you are, right? Now, so when a packet has to be sent from here to there, now these routers in the internet, they don't know anything about 2002. They have never seen an address like that, or 1001. So those addresses cannot be seen by these legacy routers. The core routers are legacy. They are the old routers. They don't understand LISP. They are LISP unaware, right? So the edge routers, what they do is they take the packet which was sent by Bob with the source address of 1001, the destination of 2002, and they encapsulate it, and they put the source as this New York and the destination as Los Angeles in the outer IP header. Now you can see that that packet will easily go through all the old routers and it will appear in Los Angeles somehow. In Los Angeles, this router will pick up that packet, and this knows that this is a LISP packet, so it will just open that and then send it to 2002 Carol. Yeah.
So how to view your locator so knows where the Carol is.
Yeah. How to do that? Okay, so that is coming up in a minute. So how do you find a locator? That is coming up in a minute. But once you know the locator, then you can just use this encapsulation. We will be using this encapsulation thing in the rest of this lecture today as well as tomorrow, the next lecture. Basically, tunneling is all that is about encapsulation. You take the packet and put into some other packet. So here we are using some IDs, but the IDs are not understood by the outside people, so we put them into the outside header where it is regular header, and then it will reach a destination which is this router. Actually, this is the address of this router, and that router will open it up and give it the packet to the destination. Okay, so the IDs look like IP addresses, so no changes to the host. Now this host doesn't really know that 1001, it knows that 1001 is the address assigned to it, so it thinks that this is its IP address, but it is the ID. That is the ID that remains the same. Even if Bob were to go to the other website, other site, it will have that 1001. So by the way, this is all very recently invented and all implemented now. So this is all in products. So let's see. Because the IDs look like IP addresses, there is no changes to the host. Hosts think that they are addresses and they just use it as they are given. Locators look like the IP addresses and therefore no changes to the core routers. The core routers don't know that this is something has been changed. They just use the IP header outside IP header. Changes are required only in the edge routers. The edge routers know that something is happening new. And the edge routers use IP to IP tunneling to send packets between the sites. Now the question is, how do you find the locator? So there is a map server which keeps track of ID to locator mapping. So map server. So basically there is some authority which knows where Bob is, where Carol is, where somebody is. When they move, they tell that authority. Basically you register. For example, in WashU, whenever we go any place, we have to register with WashU saying that I am going to this country. Okay? Or we tell our office person that I am going here. So similarly, you register with the map server, your location, and then your packets will be delivered there. Does that answer your question?
Yes.
Okay. All right. So now you see the header. This is your original packet, which was source and destination. Looks like source and destination IP, right? But these are IDs, and this is your IP payload. All that is put into a UDP header, and then that UDP packet is put inside the IP header. Okay. So basically the reason is why do you need UDP is because you need a protocol type field here. Actually, what I have not shown here is the full IP header. All I have shown is the source and destination, but there is source, destination, protocol type, and other fields in the header, right? This is complete IP header. So here the protocol type will say this is UDP, is the payload, and then UDP will open that up, and it will go from there, right? Let's see. So let's define few more terms to completely understand this thing. First is the endpoint identifier. So the ID is called EID, endpoint identifier, and it is from a different namespace. Now, what is the namespace? Basically, when you take the addresses, that is your address space. So, for example, at my home, I take the addresses from 192.168.0.1, right? At your home, you might take it from 192.168.1.1, or some other place 192.168.100.1, right? Everybody has a different piece of the address space that they use, right? Some places they use 172 something, some places they use 10 point something. So these are basically the address spaces. Now here we need ID spaces. So we could take any 32-bit number space and call it our ID space. That is our namespace. All right. And so these are not routable on global internet because these addresses like 192 and 168, etc., private addresses, those are not allowed on the internet, right? You know that, right? Private addresses are not allowed on the internet. They are allowed inside your site but not outside. So you could use them as ID, and but you register them with your DNS. So you register that this ID belongs to Bob, this ID belongs to Carol. So when you want to talk to Carol, you go to DNS and you say, what is the address for Carol? And it says 2.0.0.2. Just like the addresses. Yeah.
Here the DNS is different from the previously mentioned that server.
So actually, I think you can live with the old DNS because when you register these IDs, the DNS thinks this is an IP address. Okay, and the host thinks that this is an IP address, but this is an ID. What probably you have to change is the DSCP server. What DSCP server does is gives you the address, and it will remember that this is Bob. I got to give him 1.0.0.1 regardless of where he is, right? So everybody gets a static IP, a static ID.
So 1001 is public, right?
For example, we have put there, but the thing is, just think about any private space. And it doesn't, by the way, it doesn't have to be private either. It could be public too. You could use 128 point whatever it is public address, okay? Because it is not going to go outside. So here, in my home, I use 192, but it is not required in my home. I could use 128 something. It's just that because as long as when I send it out with the correct address. Inside I can use public or private. Right? And the reason we use private is basically so the NAT doesn't get confused. Basically the NAT knows that this is a private address and it changes it to public address and so on and so forth. But we could just use public addresses inside. Okay? NAT will have to change it to the address that the carrier has given us. Because these are not seen outside. So that's the idea. That the EID comes from a different namespace. They are not routable on the global internet. They may not be routable actually, and they are registered in the DNS. Routing locators are from the existing namespace. So what this is saying is these are the globally routable addresses. So locators are globally routable. So these numbers that we saw here, we took a wrong example. Because these are all globally routable. This 172 number is wrong. I will have to check. I think this might be, see, thing is 172 might be okay, because some part of 172 is private and some part is public.
But you're talking about the IDs which are not routable, 1001.
Those are not routable. Those may not be routable. The thing is, but these have to be, when you have the locators, they have to be public IP addresses. So 172 is probably public IP address. Okay? Remember, there are 3 private IP addresses. Anybody remembers 3 private IP addresses? 192.168.0. I think. You have to have 168. Okay? Because 167 is public. And 10 is complete available. So 10.0.0.0 is available, full, 24 bits. Or with 192, you get only 16 bits, the last 16 bits. With 172, I forget. Okay? It could be, I think it is less than one, it's more than 8 bits, but less than, so it is somewhere between there. Okay? 17. So I think this is okay then. I'm not sure. But anyway, if I change that to 128, then I'm happy with everything else, because this is all public addresses. All right? Everybody understands what I'm talking about? Okay. If not, then ask right now. All right. In ingress tunnel router, ITR receives and decapsulates, and ETR, egress tunnel router, encapsulates and transmits. So let's look at ITR and ETR. Here, this router on the right, edge router on the right, is the ITR. This takes the packet from the outside world and decapsulates it. This is an ETR. This on the left, the router on the left is ETR, because it takes a packet and encapsulates it, sends it out. Right? So you have ETR and ITR. Now everything that is ETR is probably also ITR, because for the packets coming in this direction, it is probably going to do that. But generally when you design a protocol, you don't assume that. You assume that these are 2 different functions. ITR function is a receiving function. ETR function is sending out into the world function. They could be in the same box, they could be in different boxes. Okay? So those are the names of the functions. ITR and ETR. XTR is when you have both ITR and ETR in the same box. Map server is where the ETR register their EID prefix to RLOC mappings, and they receive the map request from the mapping systems and forward them to ETRs. So basically, these routers, the tunnel routers, they use map server to register as well as to get information. That is the directory where you go, not DNS. DNS information doesn't change, but the map server information changes as people move. Okay, so now you can see, well, let me finish this line. Map resolver receives map requests from ITR and forwards them to the mapping system. So that is basically, there are 2 functions here, server and resolver. Server is where you register, and resolver is where you find the answer, where you query. Right? So you go one place and register, you go to other place to find the answer. Now again, though both the functions could be in the same place, but these are 2 functions. Okay, one is a database lookup problem, one is a database entry problem. Alright? So let's see one example here first, but then we apply it to the data center in a minute. But anyway, so again the answers, again I took some wrong examples here. I will have to change these examples. But let's assume that this domain is dual connected. This site has 2 connections. One is to provider A via this router, and it has the address 10.0008, and that address would be actually something other than 10, because you cannot have a 10 address in a public. That's a private address, right? But let's assume that let's say this is 14 or something, okay? In that case, so this is first address, and then it also has a second router which has an address 11 something. This site has also two routers. One has with provider C and its address is 12, and with provider D its address is 13 something. Now here inside there is a person 1001 which wants to talk to 2002 here. So this is the Bob, this is Carol. So when the packet goes from here, we write a packet, IP packet, which goes from 1001 to 1002. That packet, when it reaches the exit, okay, we arbitrarily or we by some reason we have to select that we have to go through provider A or provider B. There might be some policy or some reason, but anyway, for policy or reason or distance, whatever reason, you decide that we want to send it via 11 by provider B. So we take this packet which is here and we put the 11 header here. So it says source is 11001 and the destination is 13002. So we selected this source and this destination. We could have selected this source and that destination, or this source and that destination. There are many possibilities here, right? But we selected that we want to go from this side to that side by using provider B and D. So we selected this as the source and this as the destination, and now the packet can find its way in the internet and it will appear here, right? Once it comes here, there we will take out the outer header and then the original packet will be sent inside. Okay. Now when you go to DNS, all DNS will tell you that the B is at 2002. So DNS doesn't really know where B is. It all knows is that the ID of B is 2002. When you go to map server says 2002 is available by two locations, either 12 or 13. Right? At 12 the priority is 1 and weight is 50. At 13 priority is 1 and weight is 15. So basically it means that you just flip a coin and decide. It is quite possible that it could have been that the 12 has a priority 1 and this has priority 2, in which case you generally want to go via priority 1. Or the weight could be different and you want to go with the lowest weight, and so on and so forth. So each, just like in the routing table there are weights. Has anybody seen their routing table in their computer? Right? Just say route print in your computer. And it will print out a route which has the weights and how your packets will go. So same thing here, we have the weights. So basically all this information is gotten from the map server. Actually it is gotten from the map resolver, but the map server has the entry and you ask the map resolver and it tells you this. Okay, yeah.
Yeah, but here the PIDs have to be different for different people, right?
Oh, IDs have to be different. I mean, if you have people, see, look, ID is globally unique, right? Globally unique in this case means that, at least in my company, we cannot have two people have the same ID. IDs have to be unique by definition. It's like two people having the same social security number. That would be very confusing. Social security number is an ID. You cannot have two people have the same ID.
But if you use the private address, that's like the 192.
Yeah.
It's odd that the two people use the same address.
Yeah, so good point. So these two people will not use the same address because they will use these IDs when are they assigned. These are belonging to the same company. Yeah. Yeah. Right? So you will talk to the people who are in the same, basically those have the ID which are unique, right? I mean, in that whole domain. Okay. So originally, by the way, LISP was invented because there were several problems. Actually, there's a problem in the next application. So I'm going to talk about the LISP. Okay. So let's go to that. So basically, the problem was that every time you change the carrier, your address changed. So for example, if you are with AT&T and AT&T has gotten the allocation of 128 and you connect to AT&T, they give you a number which starts with 128. And then you go to Verizon and they are starting with 108. Then you have to renumber all your servers. Right? Because servers, people are going to reach those web servers, those FTP servers and all of them. Now they will have a new IP address. When you change the carrier, IP address change, and this was a big problem. And when you have site multi-homing, that was even a bigger problem. So for example, if you had one company, two carriers, AT&T and Verizon, so you get 128 from AT&T and 108 from Verizon. Now if somebody wants to send it, they have to know that this thing has two addresses. Well, now you can do very easily with LISP, but before everybody has to advertise, and it's kind of very difficult for AT&T to advertise Verizon's address, saying that you can also reach the same site by 108, and Verizon to advertise AT&T's address. So this was causing a lot of problems before, because people, when they moved, they had a problem, and when they're multi-homed, the other companies had a problem of advertising their location. Okay. Now with LISP, all this is gone because you don't change any of your addresses. Your these locators are basically what the rest of the world uses, and so you can go from carrier to carrier. All right. So now, what is the application in the data center? So this was actually invented for the outside world, for the WAN traffic, but now we are using it inside the data center. Basically, what you can do is you can have two data centers, and they could use the same kind of the ID space, and then you could have a here LISP aware router which talks to the aggregation switches, and then basically so these act as the exit, and this acts as the entry here on this side. So you see only the blue stuff here is LISP aware. These aggregation routers are LISP aware, and this XTR is LISP aware, and everything else is not aware. For example, if these core routers, they are normal IP routers, they are LISP unaware. These access could be switches or routers. If they are routers, they are LISP unaware. They don't know anything about this business going on, because they just use the internal IP addresses, and these use only external IP addresses. The core uses only external IP addresses, the access uses only internal IP addresses. It's only the aggregation routers here that know, and they encapsulate the packet when it goes out, and they decapsulate the packet when it gets in. Okay, so if you have a VM which is here, it will have an IP address. Actually, it will have an ID which will remain the same when the VM moves. You see, so we are not now. Here's the thing, though: this technology does not assume Ethernet at all. None of this, anything has to be Ethernet. It could be all IP with point-to-point links or whatever you want to have inside. Right? So this is layer 3 technology, fully layer 3 technology. Right? So you can move the VMs from one data center to another data center, but they keep the same ID, which is IP address. And notice that these IP addresses we are using just like the Ethernet addresses, where we look up the whole thing 2002, because we don't look up the prefix, because it is quite possible that 2002 is here, 2003 is over there. Right? So unlike the IP prefixes, these are IDs. We look the whole thing 32 bits match.
triangulation is located?
Eh?
When we say no triangulation after move.
No triangulation after move. So basically what happens is that comment has to do with the mobile IP. Some of you are familiar with mobile IP. I really don't think I have time here to discuss mobile IP, but in mobile IP, what happens is you have a home agent and you have a foreign agent. So whenever somebody wants to talk to you, they talk to your home agent, your secretary first. The secretary sends the packet to you. That is called triangulation, because if it so happens that you are in France and somebody in France wants to talk to you, your secretary is in United States, they have to call United States, then it has to go back to France again, to me, or to whoever, right? So that is called triangulation, because the people who want to talk are next to each other, but they have to go through somebody who is far away. Okay? That happens with mobile IP, not with this LISP. How many people know mobile IP? 1, 2, 3, little bit. And nobody else, you guys never heard of mobile IP? Yeah, so there is a big variety of 473. I mean, I don't know. I mean, like 473 we call it, but we teach all this. So I don't know what they teach in other places. Mobile IP is taught in 473 here. Okay, anyway, let's assume that we understand this part, that in a data center you could have aggregation switches which could act as your routers, egress and the ingress router, and this router you need because if the external traffic is coming, that has to be encapsulated so that these guys can decapsulate it. So you need one more router here. So we have 1, 2, 3, 4, 5 routers which are LISP aware. Everything else is LISP unaware. Even the VMs don't know that they are running LISP. VMs really use that as IP address, even though it is their ID. All right. So no IP address change and no triangulation. Push or pull. Now let's see this thing. Push or pull model for resolution. So I didn't explain that part. So when you want to find out where who is, there are two ways. First is to ask, or second is to be told. So when you need something, you need to find out where 2.0.0.2 is. You could go to the resolver and say where it is. That is called pull. You're pulling the information. Push is when the resolver sends you a big table, says that look, here is the information right now. This is where everybody is. And so that could be done generally at when the routers come up. When the XTR comes up, the resolver sends its whole bundle of information. That is the push. Right? Everybody understand push and pull? Push is the information is given to you, and pull is when you get the information by requesting it. Yeah. All right, I think we are coming to 4 o'clock, so I got to finish this summary. So the summary is that Ethernet is being extended to cover multiple data centers and large campuses. Networks are being flattened end to end. Most of the efforts encapsulate Ethernet frames and transport them using layer 3 protocols. TRILL uses IS to IS, and the LISP uses UDP, basically. And they use IP addresses. This TRILL uses MAC addresses, Ethernet addresses. So you saw two different approaches. In TRILL, we use MAC addresses as the outside header, and we send it over. And in LISP, we use the IP addresses in the outside header. Okay? Reading list is here. In fact, there is a big reference list at the end. I don't know whether I put it in yours or not. You have this reference list. Again, as I said, reference list is not really necessary to read, but make sure that you read the reading list. Okay? All right? Thank you.